Good evening, Ashok sir, and good evening, dear participants.
Yes,
Welcome,
sir. Am
welcome
I
to.
audible to you?
Yes, yes.
Okay, sir. Thank you.
Sir, you have been made a screen presenter.
Okay, sir. Now I'll
Is
present one time my PPT. Can you see, sir, whether it is there or not?
yeah, yeah.
Okay, sir. Sir, whether my screen is visible to you, sir?
Yes, yes, sir.
Okay, sir.
Please change the slides.
Yeah, sir.
Yeah, they are changing.
Okay, na, sir?
It's
Yeah.
it's okay, fine.
Okay, sir. Yeah. I'm starting presentation, sir. Yeah.
Arpita ma'am.
Sir, am I audible to you?
Yeah, yeah, audible ma'am. Please share the starting slide.
Hello.
Welcome slide.
Hello, sir. Am I audible?
Yes, ma'am. Am I audible now?
Yes, sir. You're audible, sir.
Hello.
Madam.
Sir, am I audible to you?
Yes, madam.
Okay, sir.
Are you able to hear me?
Yes, sir.
Okay, fine. Is the welcome slide visible to you? To all of you?
Yes, sir.
It's visible, sir.
Yes, sir. Yes, sir.
വീട്ടിലാണോ?
పౌలు కొరకు ముందుగా ఎవరిని పంపించాడు?
മറ്റേ ഫോൺ കയ്യിലുണ്ട്. ഇപ്പൊ SMS വരും, നോക്കണോ? മറ്റേ SMS വരുന്ന ഫോൺ ഇതിൽ തന്നെയാണോ? ഓക്കെ, എനിക്ക് നോക്കാവേ.
Okay. So it's already 6:07. Let's go ahead with the session. Good evening, my dear participants, and welcome to this session 7 of day 4 of 6 days online ATAL FDP program on advanced VLSI design and AI-enabled automation for next generation semiconductor manufacturing. Our today's distinguished speaker is Dr. T. Ashok Sir, Associate Professor, Department of ECE, NRIIT Institute of Technology. Before Ashok Sir start his presentation, our co-coordinator Madam will briefly introduce Sir to you. Later, Ashok Sir, you can proceed.
Okay, sir. Am I audible to you?
Yes, ma'am.
Okay, sir. Good evening, everyone. Good evening to all the participants. Welcome to day 4, session 7. Today we have a distinguished speaker, Dr. T. Ashok, sir, with us. So I feel honored to introduce my colleague, Dr. T. Ashok, sir. Dr. T. Ashok is currently working as an associate professor in the Department of Electronics and Communication Engineering at NRIIT Institute of Technology. He received his BTech and MTech degrees from JNTU Kakinada and was awarded his PhD from WIT AP University. With over 10 years of teaching experience, Dr. Ashok has made significant contributions to the field of semiconductor device research. His primary research interests include the design and analysis of TFET structures, as well as their applications in digital circuits, photosensing, and biosensing. He has published multiple research papers in reputed journals such as Springer, Elsevier, and IOP Science, along with presenting at various IEEE conferences. Dr. Ashok continues to contribute actively to advancing low power and high performance device technologies. Sir, I request you to continue the session.
Yes, madam. Thank you so much, madam. Such a nice brief introduction about me. And I would like to thank to all the ATAL FDP coordinators of NRIIT, Dr. Srinivas sir, and Arpita madam and HOD, all my dear faculty members and research scholars. Thank you so much for giving me this opportunity to present my work in this ATAL platform. So, let, so now I'd like to present my work. In this session, I would like to present my work on performance analysis of highly sensitive emergent tunnel FETs for detecting light in near air range. Here, I have designed some few novel TFET based photosensors, so which are able to detect light in near air range. So here, these are the contents I would like to cover in this presentation. First, introduction to photosensor. Here, I will discuss the how photosensor evolution happened from diode to TFET. Then, what is the importance of TFET? Here, importance of TFET means earlier in MOSFET and diode or transistor-based photosensor, there are some research gaps are there. So, how this TFET structure fulfilling that gaps and how it can be improve the performance of the photosensor, I'll discuss here. Then, design of TFET-based photosensor. Here, I'll take one TFET structure, my TFET structure, and I'll show how to design the photosensor with the help of this TFET structure. Next, spectral performance parameters like sensitivity and signal to noise ratio, responsivity. These things and all I'll cover in this session, in this topic. Next, emerging TFET based photosensor design. Here I'll show a few emerging TFET structures and I'll compare those structure with the existing works and my proposed work also. We'll see that later. Next, merits of the TFET based photosensor. I'll show what are the merits which can occur by the help of this TFET structure. Lastly, applications and future scope. Let's come to my presentation. First, introduction to photosensor.
Ashok
As
sir,
we all,
Ashok sir,
yes,
small interruption.
yes,
Please maximize your slides.
yeah, thank you. 1 minute. Now it's okay, sir?
Yeah, it's nice. It's nice. Please
Okay, yeah,
continue.
okay. Yeah, okay, sir. So, to design a photosensor, there is a key parameter which is called as a incident photon energy must be greater than the band energy of the semiconductor material. Let us see, if you design a photosensor or photo detector, any diode, there must be one photo absorbing substance. If you can observe from figure 1, there is a one window, we call it as a photo absorbing substance. Here we can project the light, then the incident photons which are projecting on this window, they can accelerate the valency electrons from valency band to conduction band. So to accelerate this electrons to conduction band, there must be some energy required. That energy we called as the incident energy, which can be represented in a h mu. So the h mu must be greater than the energy band gap of the material. For example, if you consider one silicon band gap of 1.2 electron volts, the incident energy must be greater than that 1.2 electron volt or equal to that 1.2 electron volt. Then only the incident photons can convert the valence electrons to convert conduction point. So here the photon energy Hv equal to 1240 divided by lambda, which is mentioned in electron volts. Here lambda is the wavelength of the light. So based on this wavelength of the light, we can decide which spectrum range our photodiode can identify. For example, visible range, near IR range, or UV range. UV range up to 350 nanometer. In visible range, it comes from 450 to 700 nanometer. Then near IR range of 750 to 1000 nanometer. So these ranges and all decided by the photo absorbing substance. That photo absorbing substance must be semiconductor material, so which may we consider maybe silicon, germanium, gallium oxide, like that. Here, if you see, figure 1 shows the photodiode. Here, we are incidenting one light into the window. The incident photons, which are having higher energy greater than the band gap of the material. So those materials can generate the electron hole pairs. So until now, here figure 2 representing the one PN junction diode, which is in reverse bias condition. Once the incident photons are deposited across the depletion region, they can create the electron hole pairs. So then it increases the electron count in the depletion region. By that, the minority charge gas count will increase. So they will create illumination current. This is the principle happened in the photodiode structure. But in diode, we are facing several problems like in junction more power dissipation is there, and also noise levels are high in the junction. PN junction diode, this and all consume more chip area. So fabricate. That's why again the technology went to the phototransistor. In phototransistor, the light mainly depositing across the base region. Here, whenever the light falls on base region, they can increase the base current. Once this base current increases, the electrons they can cross more into collector region, more enter into the collector region. Thereby, the collector current increases. This diode and phototransistors both are current control device. So, based on incident light, their current conductivity is increasing. Initially, they are keeping in reverse bias condition. So that time device in off condition. Whenever this illumination is depositing on the illumination window, light is depositing on the illumination window, then only the electrons count is increasing. By that, electrons can increase the output current. Next, when it comes to photo FET, here we are depositing they are representing the light on channel region. Once this light can create the channel region. Initially, if you consider any MOSFET structure, there is a no channel initial it will be there. Once light depositing on the channel region, there will be a channel created between the source and drain region. By that, it can increases the drain current. So these are the conventional structures based on the photosensor, conventional FET structures based photosensor, diode based photosensor, and transistor based photosensor. But main problem with this conventional one is main power dissipation is more and speed is very less. They occupy more chip area. And when it comes to FET structures, their subprocess scope is more. So to overcome or to address these all research gaps, we have chosen one new device called as a tunnel FET. If you see the tunnel FET structure, here tunnel FET is basically a gated pin diode. Here both source and drain regions are oppositely doped. Middle intrinsic region will be there. It works mainly on the principle of barrier band-to-band tunneling principle across the source and channel region. Whenever we will see the operation of tunnel FET. Here if you see source is doped with, here I have considered one NT-FET. NT-FET means the source is doped with P type and drain is doped with N type. If you tell NT-FET means drain is doped with N type impurities. Even if you tell it is a P-type T-FET, the drain is doped with P-type impurities. Source will be the always opposite to the drain impurities. Next, the channel region we are considering the intrinsic region. The figure B shows the band diagram of the channel FET. Here if you see the at source region and channel and drain region, the band alignment will be like this. Here there is no overlapping between the bands, which means device in off condition. When device in off condition, there is no overlap between the bands. Now, first, TFET, when TFET will be on? Whenever the gate voltage, if you give greater than 0 volts, then or positive volt, then only this device will on. How this device will on, we'll see. If I give the VGS greater than 0 volt, the conduction band in the channel region gets aligned with the valency band of the source region. So here conduction band, there are so many free available states are there. Once if I give voltage, gate voltage, which is greater than the 0 volt, the valency band of the source region get aligned with the channel conduction band. So the valence electrons which can directly tunnel into the channel conduction band. Then the electrons will move from source to channel region. There they'll go enter into the drain region. Like this, the TFET device will on and it will conduct the drain current. Whenever the device is 0 or whenever we apply VGS is 0, there is no band alignment is there. So no electrons in the, no valence electrons or bonded electrons in the source region can enter into the channel region. So there is no availability of states. Here, another one condition which is a drawback of TFET, which we call as a ambipolar conduction. Here, ambipolar conduction means if you give VGS is 0, the device should off. But here, what is happening if you give the input voltage or gate voltage less than 0, device should off. But here, whenever we are giving VGS less than 0, the drain conduction band gets aligned with the channel valency band. Here, the electrons in the channel valency band, they are entering into the drain conduction band. So there will be again tunneling happening. This create again increment of drain current, which is the problem in TFETs. If we need to avoid this problem, we should increase the band gap across the channel and drain region. Then only we can avoid this ambipolar conduction. So if you see TFET operation, in this TFET, three conditions are there. Whenever VGS is 0, the device in off state. If you give VGS greater than 0, the device in on state. If you give VGS less than 0, more less than or more negative voltage, there will be ambipolar conduction in the device. So let's see what are the merits of tunnel FET when compared to MOSFET. How TFET is good when compared to MOSFET. If you see here MOSFET structure, nowadays when our technology nodes comes down to below 35 nanometer, which means the channel length goes below the 35 nanometer. There is a problems called as short channel effects which are occurring in the MOSFET device. The short channel effects are mainly classified into drain-induced barrier lowering, gate-induced drain leakage, hot electron effect, velocity saturation. Like already earlier session, our faculty maybe they have discussed you. In these short channel effects, they can increase the device off-state current, which is also called as a leakage current in the device. So this leakage current makes more power dissipation in the devices. So we need to avoid those conditions. That's why we prefer the tunnel effect. Here the mechanism is entirely different. If you see figure 7, here first two things are indicates MOSFET and T-FET structure. Here source and drain region of the MOSFET are similarly doped, but in T-FET source and drain regions are oppositely doped. That's why their band alignment are also different. If you see here, the source and drain regions of the MOSFET bands are almost similar, but channel region, the valency conduction band is so far away from the valency band. So here, what is happening? Whenever the electrons has to enter into the conduction band, it has to overcome the barrier across the source and drain region. Means initially, electron has to enter in the conduction band, then only they can overcome the barrier and entering into the conduction band. This over this voltage required voltage to overcome this barrier we called as a minimum thermodynamic voltage or thermodynamic limit. In MOSFET, that thermodynamic limit is 60 millivolts per decade. So to we can't able to avoid this limitation in MOSFET. But when it comes to DFET, there is a no limitation of overcoming the barrier. Here, whenever the VGS is greater than 0, the valence conduction band of the channel region, it gets aligned with the source valency band. So the bounded electrons or valence electrons in the source region, they are entering into the conduction band of the tunnel FET easily. Here, mainly deciding factor is the barrier band gap across the source and the channel region, which decide how electrons has to enter into the conduction band. So this thermodynamic limit due to thermodynamic limitation, subthreshold swing is more in MOSFET structures. When it comes to tunnel FET, there is a no limitation on there is a no thermodynamic limit. That's why we can reduce the subthreshold swing below the 60 millivolts per decade also. Here, what is meant by subthreshold swing? Subthreshold swing is the minimum gate voltage required to turn on or turn off the device, which means the minimum gate voltage required to increase 1 decade change in the drain current, increase or decrease the 1 decade drain current. Next, as the increment of short channel effects, it requires uh, more power dissipation in MOSFET. But here tunnel FET requires less low supply voltage. Next, low static power dissipation. In tunnel FET, there is no short channel effect, so static power dissipation also very less. Next, better switching performance. The subthreshold swing of the tunnel FET is very low, so it will show better switching performance. Next, because of this less SSI subthreshold average, tunnel FET can be suitable for high-speed operations also. Next, the structure or architecture are almost similar to the MOSFET only. That's why this tunnel FET can be compatible to the CMOS technology. If you see MOSFET and tunnel FET, the only difference is the doping regions only. Remaining all the area, everything under same. That's why we can easily compact the current CMOS technology, or we can easily replace the current CMOS technology with this tunnel FET. Next, what are the parameters which decide the tunneling of the carrier from source valency into band to the channel conduction band. If you see this prefix structure, the tunneling property is mainly depends upon the band gap across the source and channel region. Here we are proposing one formula. There is one formula for this one. Channel screen length, which decides how many electrons they can enter into the conduction band, which is mainly the tunneling property we can increase by reducing this barrier width across the source and channel region. Then for this one, we required the steep doping profile across the source region and channel region, or a strong electrostatic field we should apply from the gate region. So this can reduce the band gap across the source and channel region. Once this band gap reduced across the source and channel region, there is a tunneling rate will be increases. Once the tunneling rate increases, the drain current will be automatically increase in the device. Now we see some small major drawbacks in the TFET are mainly low on current and ambipolar conduction. These two are the main problems. We can avoid these problems by showing, and we are showing some solutions also. If you see here, low on current mainly due to the more barrier width across the source and channel region. Here, source and channel region, if there is a more barrier width between the source and the channel region, there is a less tunneling property. Because of this one, on current is reducing in a TFET device, conventional TFET device. Nowadays, many emerging structures are came. They can avoid these things by implementing few techniques. If you see these techniques, here we are implementing some narrow band gap source materials. Means across the source and channel region, some small band gap materials we can by inserting the small band gap material, they can reduce the barrier width across the source and channel region. Next, to increasing the source doping level. By increasing the source doping level, the channel source conduction band will little bit comes down towards the valency band and high K gate dielectric. What this high K gate dielectric will make, whenever we are using gate dielectric material as a high K materials, they can allow more electric field towards the channel region. Once the electric field which comes towards the channel region increases, more band bending happening. So this increment of band bending that can increase the tunneling property of the device. Next, by using the heavily doped pockets across the source and between the source channel region. Next, by doing the work function engineering. Work function engineering means the gate region we can split into two models. Here, if you see figure 7 TFET structure, the gate region we can split into the two metal region. One we can give some high work function, other one low work function. By varying this work function of metal region, that can modulate the electric field which is applied towards the channel region. Once the portion across the source and drain region increases the electric field, that creates more bending across the source and channel region. Once this band bending occurs more, so more portion of the electrons they can enter into the channel conduction region. Here mainly the tunneling rate mainly depends upon how much portion of the uh, channel conduction band gets overlapped with source valency band. If more overlapping is more, then more number of electrons will be tunneling into the channel region. By the drain current is increasing. Next, these all are the techniques which can improve the or which can resolve the low on current problem in TFET. When it comes to the ambipolar conduction, we need to increase the channel drain energy band gap or channel drain band region. Here, if you see the channel and drain region, if you give lesser gate voltage, it should not be overlapped. We need to create more band gap across the channel and drain region, channel drain interface region. For that, to increasing the band gap, we are using few techniques like that we are increasing the drain doping level more and increasing the oxide thickness across the channel drain interface. It allows very less electric field across the channel drain interface. By that, less overlapping is occurring across the channel and channel valency band, drain conduction band. By that, very few electrons can tunnel into the drain conduction band during the ambipolar condition. Next, wide band gap material. It is just the opposite, like how we are solving the on current problem. Here, we are giving some high band gap material across the drain region. So this high band gap material creates or increases the band gap across the channel drain interface. By that, it can resolve the ambipolar conduction problem. Next, gate drain underlap, or we are the drain is underlapped with the gate region. Gate is underlapped with the drain region. That's a very less electric field applied across the channel drain interface. By that, band gap is increases more. Next, low K dielectric. We providing the low K dielectric upon the channel drain interface, which allow very less electric field towards the channel region. That can overcome the ambipolar conduction problem. Next, so now we are choosing TFET as a photosensor. Before that, we are overcoming the TFET drawbacks and all by implementing these techniques, and we are going towards the TFET photosensor design. If you see here, this is my proposed structure and my first publication paper on photosensor. I have published this paper on micron nanostructure. Which is elsewhere journal. Here, if you see, this is my TFET. Here, what I have chosen a dual line tunneling. It is a dual line tunneling based elevated source TFET. Here, I have chosen my drain channel and source region. Here, source is doped with P-type, channel is intrinsic, and drain is doped with N-type region. Here, I elevated my source region little bit upward side, and similarly, my gate region also increased, and the bottom gate of the channel region extend towards the source region. Why I have made all these things means my target is to increase the line tunneling. Once the line tunneling increases, this gives very less subthreshold swing and very high on current. If you see here, the here I placed one pocket across the source and channel region. One heavily doped N-type pocket I placed between the channel, which is colored with intrinsic silicon or green color, and my source region, which is a this pink color one. Here I placed one yellow color pocket, this N plus pocket across the source between the source and channel region. This pocket creates the makes lower band gap or provides the less band gap across the source and channel region. Because of this reduction in band gap across the source and channel region, more electrons they can tunnel into the channel region. Once this tunneling rate increases, there is a more increment of drain current in the device. If you see here, the gate potential, which helps in producing the line tunneling in both direction, X and Y direction. By that, the tunneling area increases. Once tunneling area increases, it should be suitable for producing less subthreshold swing. Here, for this to design a TFET based photosensor, I have used one moderately doped silicon top gate. Here I have used top gate, which is a photo absorbing substance, which is moderately doped with N-type silicon. Once the light is incident on this gate material or photo absorbing substance, the incident photons will create the electron hole pairs in the gate region. Here in TFET, this mechanism is entirely different with the photodiodes or phototransistors. They can increase the current in the device, but here whenever we are depositing the light in this device, they can create the electron hole pair. They can improve the optical voltage, which is added to the gate voltage. By that, the band bending is more in this device. Here, here I have maintained the energy band gap of the photo absorbing material should be less than the incident light energy, or incident light energy I have taken more when compared to the gate, that photo absorbing gate. Here any photo sensor we should have two conditions. One is light condition, another one is dark condition. Whenever light is falling on the gate, that time here whenever the light is falling 90 degrees, this time we can take it as a light condition. When light is incident on the or polarizing on the gate in a horizontal direction or 180 degree direction, we can consider it is a dark condition. So here I have taken, we have used the center STCAD software for doing all this device simulation and all. For this, I have used one complex refractive index in the device file. So in that complex refractive index, there is excitation window and solver session will be there. In that excitation window, we are providing the polarization angle and incident energy and wavelength of the light and all. We are providing that excitation window. Next, this optical solver session will solve all the simulations and all. Based on this one, they gives the optical generation rate. Next, spectral for once this design completed, we are observing the how what are the performance parameter of this defect based photo sensor. Here mainly optical generation rate. What is mean by optical generation rate? The optical generation rate refers to the rate of electron holes pairs are generated in the inside the device due to absorption of incident photons. Once photons are incident on the photo absorbing substance, how many electron hole pairs are successfully generated? If incident energy is less than the uh, band gap of the photo absorbing material, it can't create the electron hole pairs. Once the incident energy greater than the EG or Hc by lambda value is greater than the EG, then only they can create the electron hole pair. So this optical generation rate indicates how many electron pairs hole pairs are generated when incident photons are fall on the absorbing substance. Here my device I designed for the to detect light in near air range. For that I consider light range from 750 nanometer to 1050 nanometer. Uh, Whenever if you see the light at lower nanometer range, it provides high instant energy. When it goes to the 1050 nanometer, the instant energy will be less. If the incident energy is more, it generates more optical generation. Then when it goes to the uh, uh, higher wavelength, the optical generation rate is less. Here, first figure B shows the dark shade condition. Means there is no light falling on the device. If there is no light falling on the device, the hole and electron Fermi levels both are merged. There is no separation or no optical voltage generated in the device. Next, see if you see the light state here, whenever the photons incident on the photo absorbing substance, the electron and hole Fermi levels get separated. If you see based on the incident, the separation is more. At lower wavelength, the hole and electron Fermi levels are more, separation more when compared to the higher wavelength. Here see when it goes to lambda at 1050 nanometer, there is a very less separation between the electron and hole Fermi levels. Once this separation is more, it creates more optical voltage in the device. Once this optical voltage can add it into the gate voltage, it can change the device performance. If you see here in this drawing here for next one of the another parameter is spectral sensitivity. Sensitivity means the ability to detect the change in light. Means it has to observe the light variations effectively. So spectral sensitivity indicates the effectiveness of the photosensor while distinguishing the narrow spaced spectral wavelengths under low light condition. If light condition also less also, it has to distinguish the different wavelength. Means it should give better performance when we are wearing the wavelength of the light. Here, if you see, we have varied the wavelength from 750 to 1050 nanometers. Initially, in dark state condition means no light state. Then our device off state current is 10 power minus 18, and I off is 10 power minus 18, and ion is nearly 10 power of minus 7. Whenever if I give the incident light energy, that time there is a optical voltage generated in the device which added through the input gate voltage. So it means it will increase more gate voltage towards the device. Once this gate voltage increases, there is a uh, more band bending across the source and channel region, which increases the tunneling rate, thereby drain current also. Like this, if I increasing the if we have lower wavelength, incident energy is more, and it gives better on current or better drain current when compared to the high wavelength. When wavelength goes increases, a very less optical voltage is generated because very less separation between the Fermi levels of holes and electron. So less optical voltage is generated. Once optical voltage is low, very less drain current is induced in the device. Like this, based on the wavelength of the light, the drain current is varied in the device. Next, come to spectral sensitivity. The spectral sensitivity we are calculating between the lower wavelength and higher wavelength. At 750 lower wavelength, for this formula is ID lambda 1 minus ID lambda 2 divided by ID lambda 2. Here lambda 1 is the 750 nanometer, and lambda 2 we have considered 1050 nanometer. So by giving this ratio, we can estimate the spectral performance. My device, we got more spectral sensitivity up to 56 or 54 at gate voltage between the 0.2 volts at 0.2 volts. Whenever if you increase the gate voltage, higher voltage, the spectral sensitivity gets reducing. Next, signal to noise ratio. Signal to noise ratio defines the noise level in the photosensor while detecting the indicate incident light. Means if your device presents more dark state current, the device becomes noisy. So there is a less dark state current in the device, which improves the signal to noise ratio high. So there are some factors which influence the signal to noise ratio, mainly based on materials, fabrication, and environmental condition. They will decide the signal to noise ratio. Here, our device, due to lower dark current, which means up to in order of 10 power minus 18, we can achieve more signal to noise ratio. Once signal to noise ratio is high, the device having very noise level in the device is very low. Here, my device at 750 nanometer, the signal to noise ratio is high. When it goes to the higher wavelength, the SNR ratio is reducing. Here, by observing this picture, we can estimate this. Next, quantum efficiency. This quantum efficiency determines how effectively incident photons are converted into the electron hole pairs. Means I already told how if all incident photons can't able to generate electron hole pairs. All are having higher energy, more energy than the material band gap. They only can generate the electron hole pair. So based on this formula, we have calculated the quantum efficiency. We found quantum efficiency more at 1050 nanometer because at 1050 nanometer, the incident photons are very less and electron hole pairs generation is more. That's why you got the quantum efficiency high. Once quantum efficiency high, the responsivity is also high because The responsibility determines how effectively incident optical power converted into the photocurrent. See here R equal to generated photocurrent with respect to the incident optical power. Here N indicates the efficiency. So quantum efficiency. If quantum efficiency more, the responsibility also high. Here Q is the charge of electron and lambda is the wavelength. Benchmark. Here my proposed device I compared with the another TFET based device, photosensor device. I found more sensitivity when compared to the existing optically gated TFET, which I will show later. And optoelectronic TFET, elevated source and dual mask gap when compared to all this earlier existing structure, except dual mask gap, my proposed structure is giving good sensitivity. When it comes to the signal to noise to ratio, due to the reduction of dark state current and improvement of ion ratio, my device getting more signal to noise ratio, which is up to 66.4. So here we are concluding the remarks. My device showing spectral sensitivity up to 54 and signal to noise ratio, which is reported as high as 6.4 dB. Next, quantum efficiency also 74%. This is my paper published on the Micron Nanostructure Journal. Next, let's see some emerging TFET structures, emerging TFET based photosensor structure. Recently, Vandana Devi and et al. They have published one paper which is based on this TFET based photosensor. Here, they have used one germanium pocket across the channel and source interface. So this germanium pocket makes more band bending across the source and channel region. Once this band bending is more, it can improve the tunneling probability by the on current in the device, and also subthreshold swing also it can improve. I'll show their paper. What are the improvements they got by providing this structure, and they shown one gate. They have considered one silicon gate above the SiO2 meter. Here, this silicon gate it will absorb the photon. Once this when light uh, incident towards the gate region, it can create the electron hole pair in the gate region. The increment of electron hole pair in the device, it can induce more optical voltage. Once this optical voltage is increases, the optical voltage gets added to the input gate voltage. It creates more band bending across the source and channel region. By that, more number of electrons they can tunnel into the channel region during the light state region. I'll show the structure in one paper. They have what are the improvements they have found. In this paper, here they are incidenting light on this silicon gate. By that, they are showing the how electron hole pairs are valence electron and hole pair level gets separated. So due to this separation, there is a more band bending across the source channel interface. By that, their drain current is increases up to 10 power of minus 15 or 10 power minus 14 when compared to the low condition. But their on current is reaching up to 10 power of minus 7. When it comes to our structure, there is a more on current. Next, spectral sensitivity. Here, if you see here, band bending is more when illumination dark condition. In figure B, it shows the more band bending when compared to the dark state condition. So once this band bending is more, their on current is also increasing. We so they have calculated the spectral sensitivity they achieved spectral sensitivity up to 25. Next, some another structure if you see here, extended dual source double gate structure of tunnel plate. This is published by the Pooja Ghosh and ATAL. Here they have taken two source region and channel region which is surrounding across the source region. Here the main target is to achieve the line tunneling. Here they placed thin channel region between the source and gate region. It makes the gate enhances the line tunneling from source to channel region, and this can increase the device tunneling rate. By that on current is high in their devices. They have placed the photosensitive gate across their back gate region. Here, this yellow color portion indicates the photo absorbing substance. They are incidenting light in the back region of this gate. Once the light falls on this gate, it can create more uh, electron hole pairs. By that, their optical gate voltage gets increases. Once optical voltage is increases, the which is added additional to the gate region, and there is more bending across the channel and source region, which can increase the drain current and all the other parameters like a sensitivity and SNR ratio. Here, their paper also I'll show. Here, this is their structure, and they shown by incidenting, they have considered the wavelength from 700 to 1100 nanometer. As at lower wavelength, their optical generation is more because of the high incident energy. Once it goes to the higher wavelength, the optical generation rate is less. Moreover, at low nanometer, the on current is going high when compared to the state condition. They have achieved spectral sensitivity of only 2. When compared to our structure, we have achieved up to 54. In Vandana Devi and all, they achieved 25. This is band diagram indicates the separation of electron and hole Fermi levels during the dark state illumination condition. They shown very less separation between the electron and hole Fermi level. Because of this less separation, very less optical voltage injures in the gate region, which creates very less band bending across the source and channel region. Next, this my another paper, which is published in the Springer publisher, the Material Science Journal. Here, we have considered another TFA structure. If you see here, an L-shaped pocket which is placed above the source region and in between the gate below the oxide region. Here, elevated source and the pocket region which is uh, surrounded across the source region can enhance the line tunneling. Here the gate can enhance the light tunneling in a horizontal direction, and top gate also enhance the line tunneling in a vertical direction. So because of this structure, our line tunneling area is more. Moreover, less off-state current in this structure. Here, because of the low corner effects, the structure creates very less off-state leakage. Here, we have placed one silicon-based, N-type silicon-based photo-absorbing substance above the source region. Whenever instant light falls on this device, there is a electron hole spacer generated across the device. Based on instant wavelength energy, the electron hole pair count increases. Later, it creates more optical voltage in the device. By that, our drain current is improving. These are the fabrication steps we follow to make this device also. Here we are depositing initially one intrinsic silicon on SiO2 material, then etching selectively on the portion to deposit gate region. Then we are depositing the P plus ions to create the source region. After that, again intrinsic silicon region is deposited. Then oxide region is deposited on the intrinsic silicon material. Then we place again the N plus ion implementation. After that, we again deposit intrinsic silicon on the top of the SiO2 material, then which is also doped with N-type silicon material. Then finally metallization step happened. After that, the device is ready to eliminate the light. Here we have considered 750 to 1050 nanometer for creating optical generation. Same at 750 nanometer, optical generation rate is more. When it goes to the 1050 nanometer, the optical generation is less. And initially, during dark condition, there is a no separation between the Fermi levels. If you see red and black lines, there is no separation between the red and black lines. Those are gets measured here. Once light falling on the device, there is a separation between the electron and hole Fermi levels. The separation between electron and hole Fermi levels is also high at 750 lower nanometer. When it goes to the 1050 nanometer, the separation is less. This separation only makes the device optical voltage, which it will decide the device optical voltage. Once this separation is more optical voltage will generate in the device. Then it can more band overlapping across the source and channel interface between source channel interface. By that, more number of electrons can tunnel into the channel region. So this EBTB electron band-to-band tunneling rate is also increasing while increasing the gate voltage from 0 to 0.3 volts. At 0 volt, less electron band-to-band tunneling rate. When it goes to the higher gate voltage, the EBTBT rate also increases more. Next, we have considered the gate oxide as a two oxide region. One is SiO2 and another one is we replaced with HFO2. Why means to enhance the electric field across the tunneling region, we have considered another material called HFO2, which is a high K dielectric material. It can increase the on current. And we shown the performance difference between the both high K and low K material. This SiO2 is a low K material, and HFO2 is a high K material. We shown the EBT-BT rate difference between the high K and low K material. At SiO2, for SiO2 material, we achieved very less EBT-BT rate when compared to HFO2. After this, we have calculated the sensitivity at different light conditions, on current, SS average, dark current, then spectral sensitivity for SiO2 material and HFO2 material. We achieved more spectral sensitivity up to 200 for the HFO2 material when compared to SiO2 material. At a different instant of light. And also SNR ratio also high for this when compared to SNR ratio. SNR ratio is high for SiO2. Why? Because SiO2 metal induces less off-state leakage when compared to HFO2. HFO2 metal gives more off-state leakage. Because of this high off-state leakage, ion by IF ratio is less. So signal to noise ratio also very less in case of HFO2. When in case of SiO2, SNR ratio is more because of the lower off-state leakage. Then again we calculate the quantum efficiency and responsivity for this. Last, another emerging structure is the which is published by Shreyas Tiwari et al., which is the split source horizontal pocket jet-shaped tunnel pit structure. Here, he consider two types of source region. One is N plus region, another one P plus region. Next, another structure he has taken one source region as a P plus source region, and another one is germanium based source region. These are source engineering techniques and all mainly to reduce the channel source channel band band energy across the source channel region. So by that, more band bending occurs across the source channel interface. So more tunneling of the more number of electrons can enter into the channel region. By that, on current is improving. Moreover, there is no pocket they have placed between the channel and drain region. It can avoid the ambipolar condition. Here he has taken two types of oxide materials, HFO2 and SiO2. This HFO2 material increases the electric field towards the source region, which also boost up the on current. If you see his paper, Shreyas Tiwari and all, he shown the band bending for illumination and dark state. Here in this figure B indicates the dark state. Here there is no. Here there is a band overlapping between the Fermi levels of electron holes. When in light state, there is a separation of bands between the holes and the electron Fermi level, which is also varying by the variation of material like this first A and C structure, A, B structures indicate the T-FET based photosensor and CD structures indicate the Z-shaped T-FET structure. He compared both things and he shown how the performance of the photosensor improved. He shown better for the HS T-FET. Heterosexual T-FET is showing the heterosexual means the source region is making of P plus and germanium materials and silicon and germanium. If two different materials we are depositing one above another, it forms heterostructure. So this heterostructure based T-FET is improving the device performance when compared to this Z-shaped T-FET. Is shown the all performance things and all here. Is shown improvement in the spectral sensitivity for heterostructure T-FET and signal to noise ratio also high in heterostructure based T-FET when compared to ZHP. And he shown responsivity and quantum efficiencies. So merits of the T-FET based photosensor. So till now these four emerging structures they are showing by doing the engineering across these four T-FET structure they are doing source engineering means they are keeping some heavily doped or low band gap material across the source channel interface. By that increasing the band bending across the source channel interface, it can improve the tunneling probability. Next, by improving the line tunneling area, which means the gate which is above the channel region can enhance the line tunneling region. So this structure by surrounding the channel region across the source region, it can enhance the line tunneling. So they are trying to improve the line tunneling. By that, it can enhance the spectral sensitivity of the device. Here, my structure also, I have used one heavily doped pocket across the source region, which can enhance the band bending more across the source and channel region. By that, we can achieve a more tunneling rate. in the device. Here they are using some microstructure. These all structure, their main target is to increase the tunneling probability of the device. By that, it can enhance the subthreshold swing. It can reduce the subthreshold swing. That will improve the device sensitivity. And also, they are trying to reduce the off-state leakage. It can reduces the dark state current. Once dark state current is reduces, there is a improvement in signal to noise ratio. Then the usage of photo-absorbing substance across the more area of the device that can improve the device response, device quantum efficiency and the responsivity of the devices. So based on this TFET based photo, merits of the TFET based photo sensor. If you see very low power consumption, it shows better performance in dark or low light conditions. TFET based device have very less off-state leakage. That's why dark current also very less. And improvement in signal to noise ratio, because less dark current or low off-state current gives low dark current. By that, signal to noise ratio is improving. Next, sharp turn on voltage, which is also called as threshold voltage, which means very lesser gate voltage device is turning on. So this will increases the device speed. So next, compact integration. The TFETs are compatible with the CMOS process. So they can allow them to the integrate into the present existing imaging systems or present architectures. Next, material versatility. It can the TFETs can be designed with the help of heterojunctions like a silicon germanium combination, gallium arsenide combination, indium gallium arsenide combination. We can design the TFET devices, and another 2D materials like a MOS2, molybdenum disulfide, and they can provide flexibility to the operate in different spectral ranges. Based on our device substance, absorbing substance, we can decide the light detection range in near IR or UV or visible range and all. By deciding the photo absorbing substance and material speed, we can decide this which range our device should operate as a photo sensor. Next, application. When comes to the applications, we can use our defect structures in low light endoscopy, because at low intensity also it can identify the photons very well. Next, security surveillance, night IR light, night vision, motion detection and all. Next, IoT smart cities, energy efficient environment monitoring, low space telescope, on optical sensors. These and all are applications of the our photo sensor. Future scope. Here, by incorporating the 2D material or group 3 semiconductors can improve the CFET based photosensor performance. Because means 2D material like if you see MOS2 or organic fits, these can give us the flexibility to our devices. So now recent technology evaluating towards the organic fits, which means flexible electronics device. So our this can be used as a sensor which are flexible towards the or which can improve the compactness or comfortability of the devices. Next, moreover, by implementing this 2D material or incorporating this 2D material and group 3-5 materials into the devices, which can become the alternative to the conventional CMOS image sensors, and especially in low power and spectral application. Here, one more thing I would like to discuss in one of my structural advantages is the corner effect. Nowadays, there is a offstate leakage from the source to channel region, because when if you use the heavily doped uh, when the gate region is overlapping across the source and channel region, there is a leakage called corner effects. Means from short source edges, some electrons which are leaking from the source edges into the channel region. To avoid this condition, we have placed one L-shaped pocket here. This can reduce the corner effects in the devices. So once this corner effect also reduced means device can give very less off-state leakage. Thank you so much, sir. Now the dais is open for queries.
Okay, thank you, Ashok sir.
Thanks.
Now this session is open for questions from participants, please.
Sir, good evening. I am Murali.
Hello, sir.
So,
Good
let me
evening.
know the difference.
Yeah,
Hi,
sir.
sir.
Tell me, sir.
Yes,
Good
sir.
evening.
Yes, sir. Please continue.
Okay. Sir, Sandeep Gautam, this side from Dehradun, Uttarakhand.
Yeah,
Today,
sir.
sir,
Tell me.
I've joined your session. It was really a very fruitful session for me because I'm working on
Okay.
tunnel flat, right? But
Okay, yes, sir.
basically, I'm working on Silvaco TCAT tool. So
Okay,
if we
sir.
want to make some kind of the photo detector or photo sensor, so which kind of the tool we have to use, sir? I couldn't
Sir, do you have
understand.
for you center sticker availability is there, sir, for you?
Centrorus.
Yes, sir.
Okay, and what about Silvaco ticket? Can we use
Yeah,
Silvaco
Silvaco
ticket?
also, you just go to the manual, Silvaco manual.
Yeah.
There you go to monochromatic source session or
Okay.
optical calculation session you go. There
Uh,
you take some complex refractive index session to polarize some for instant slides and all. There you can have some excitation session will be there and optical solver sessions should be there. You have to add these things and all. But actually, I don't have idea on Silvaco tool. Actually, I worked on Centrus tool. That's why I can't able to tell where these things and all there and all.
okay. Right, sir.
But
Right.
if you use the center sticker, the whatever I told, those things and all there in a user manual only. Just copy those things and paste. You try to simulate those things.
Okay. So Centrorus is same like a Silvaco that we have to write the script and then after simulation process is going on, right?
Yeah, everything's same, sir. But few keywords will be changed. There, you need
Okay.
to do everywhere meshing. In Centeras, you will do at the end of the all device dimensions only. You will give meshing. Only one statement itself you can give meshing. But your Silvaco, you are giving every statement. There is meshing you are giving, right?
Okay, sir. Okay. Yeah. Thank you so
Hmm.
much. So much, sir.
Yeah. Okay, sir.
Sir, what is the major differences between FinFETs to the TFETs of philosophy? Both are right
Yeah,
now
sir.
using in the real-time application.
Yeah, sir.
Just I want to know.
Yeah, sir. More or less, sir. Actually, in FinFET, I'll show one MOSFET diagram. In here, in figure 7, are you observing the MOSFET diagram, sir? Murli, sir, are
Yes,
you there?
yes, sir, yes, sir. Yes, we
1
continue, sir.
minute. Yeah. Here, in MOSFET, this is a single gate MOSFET. Means the gate is only top of the P minus region. Means which is a channel region. Only top of the channel region. It is called as a single gate MOSFET. Once we place another gate in bottom side of this P region, we call it as a double gate MOSFET. If you keep this gate region on another side, means front side of the this one means that is a tri-gate. This tri-gate MOSFETs we also called as a FinFETs. Okay, sir. This is a device. This is a design variation. Means the gate is surrounding three sides of the channel region that we call as a tri-gate or FinFET. Here, when this whatever gates we are increasing gate count means we are increasing the gate region that by that we are giving we are reducing the short channel effects, means more gate controllability. If you are increasing gate controllability more, means less short channel effects will occur. If devices become short channel, short or channel region becomes short, there is a chance of more short channel can occur, short channel effects can occur. But we are surrounding this gate region. By that increasing the gate control, you are you are trying to reducing the short channel effects. But it is not that much attempt it can control. But when it comes to the tunnel fate, here if you take only gate and one region also, there is a no link with this short channel effects, because here carriers are mainly based on the tunneling, band to band tunneling. Once the channel conduction band gets overlapped with source valency band, then only the electrons can tunnel into the channel region. Until that device is off state only, no leakage will be there. Main region. If you reduce the channel dimension also, there is a no leakage between the source and channel region because of this provision of this energy band gap across the source and channel region. If this band gap is less, means there is a chance of electrons can tunnel into the channel region. But we are modulating that source channel interface by keeping some pockets and lower band gap material. By that we are modulating those regions.
Okay, okay,
So
sir.
main reason is
Can
FinFET, even FinFET also short channel effects will occur, but in tunnel FET we are avoiding the short channel effects. Once short channel effects are avoided, there is a very less leakage in the device. If short channel effects are present, there is high leakage in the device.
okay, sir. Can we apply multiple gates around to the T-FET targets, sir?
Tunnel FET, sir?
Yes.
Yeah, we can apply.
Like
Yeah,
gate mask.
in tunnel FET also, we are keeping bottom side gate also. But if here we are keeping bottom side gate, means there should be some meaning. I'll show on my structure. Here, see, sir. Here I have placed another gate. If you see, here top one gate is there. Bottom also I have placed another gate, which means what? This here, what purpose I made this? I kept this bottom gate, means I need to increase the line tunneling. That's why. If gate is above the pocket, then only line tunneling will occur. If there is no gate above the pocket region, there no line tunneling will occur. So to getting line tunneling only, I placed this bottom gate above I extend this bottom gate towards the source region. And also if you see this top gate also, I elevated above the source region. What it makes, it is making enhancing the line tunneling towards the pocket region in horizontal direction. This bottom gate enhancing the line tunneling towards the downside. So both x direction and y direction line tunneling is occurring. It means more tunneling area is provided here. Once the tunneling area increases, means device tunneling probability is more. Once a high number of electrons are tunneling into the channel region, more drain current will increases. So if the drain current increases very fastly, drain current increases means spectral sensitivity also increases, because subthreshold swing is very less. With a very less gate voltage, device will be turned on. Murali sir, are you clear that?
Okay, sir.
Okay, Ashok sir, there are 3 more questions in the chat. I will read out. You please answer.
Yeah, yes, sir.
Which tool is being used for simulation?
Yeah, we are using center as TCAD, sir, for simulation. But in center as TCAD simulation, there is a 3 files will be there. One is design file or parameter file. Next, device file will be there, and design file. In that design file, we are mentioning the all geometry, the device dimensions and all. First, the design file we are mentioned, but in the device function file, we need to keep the photo sensor session. That means we need to select one monochromatic source and complex refractive index we need to take. In that complex refractive index, we need to add excitation window and optical solver sessions and all. Once this process and all if you complete, means then only that can be worked as a photosensor. Then only we can simulate the photosensor device.
Okay. So another question on TFET speed. The
Yes,
question
sir.
is, does TFET works under gigahertz or terahertz speed?
Yeah, sir. It depends upon the subthreshold swing, sir. Subthreshold swing means uh, how much based on tunneling rate. Subthreshold swing it is depends on. If device having more tunneling rate and very less subthreshold swing, that device may suitable for up to terahertz, up to megahertz range. I have idea, but terahertz I don't know. Up to gigahertz, whether it will work or not, I don't know. Yeah,
Okay.
but
Another
by
question. Yeah, please go ahead.
yeah, but we are trying to reduce the off-state leakage, and we need to improve the uh, on current, then reduce the subthreshold swing. These three parameters will decide the device speed. Only mainly subthreshold swing. We need to reduce subthreshold swing means device will work faster.
Okay, one more question. Sir, where will we get the model file of TFET?
Yes, that's what I told. They has to go to the monochromatic source session is there. In center streaked manual, monochromatic source session is there. They has to go to the session. There they need to select different files are there. Their optical solver session they has to include, and excitation window they has to include. Uh, Here that's why I mentioned. First of all, they has to select the complex refractive index model. In that model, they should keep the excitation window. In that excitation window, they has to select polarization angle, incident energy, and wavelength of the light. So by providing all these things, later they can simulate the device.
Okay. So one last question from the participants.
Yes.
Is this TFET has fab support?
No, sir, I didn't get. Is this pivot have?
Fab
This
support,
TFET
maybe
is fab
fabrication they are
support.
talking about.
Fabs, yeah, sir. Already now fabrication labs they are implementing TFET structure. Only difference between MOSFET and TFET is only difference only source and drain region. There in MOSFET, source and drain regions are doped similarly, but here source dopants are opposite to the drain dopants in TFET structure. So remaining everything same. Now, what are the existing these fab labs? They can fabricate TFET also. Already, uh, TSM Taiwan Semiconductor Manufacturing Company they are implementing TFET based TFETs also. They are made TFET based chips also.
Okay.
Sir, you have one more question that is posted in the chat.
Yeah, madam.
What other emerging devices are available in that tool that you have mentioned?
Yes, sir. Now, Centristic tool is supporting the 2D materials also. Nowadays, mainly research is going towards the 2D materials like MOS2 material and dicharcoalide, charcoalide. Those materials they are including in the source or gate regions. By that, they can improve the photosensor performance also. They for if they want to select those 2D material means they has to change the material files, material parameter file. They has to go to Centra's material parameter file. They need to include the uh, those things. They has to include their band gap and that material parameter things and all. They has to include in that material file. Then only they can use that materials. So better nowadays research going on organic fats and this 2D material based defect. Now that research is going on more.
Okay, sir. One question from my end at the basic level. What are the materials used to improve the TFET performance, sir?
Generally to uh, keep more fabrication support. Now I done all my works on silicon based only, sir. because availability of silicon is more and fabrication also it include very less complex. That's why I made all my structures based on silicon only. But few members they are including germanium, some compound materials like indium gallium arsenide and all. But their fabrication is little bit more. It takes more thermal cost, and also some of them they're using some carbon nanotubes, these things and all. The fabrication of those carbon nanotubes also very tough because it will take more thermal cost. Means their doping and all also very tough in fabrication when compared to silicon. My suggestion first to go to silicon, then they whenever it required means they can use some compound materials or low band gap material, that will be good.
Okay. Okay, thank you, sir. Dear
Yes.
participants, any more questions or shall we wind up the session?
Wind up, sir.
Okay, if there are no questions, we shall wind up this session because the resource person of the next session has already joined us.
Yeah.
Thank you, Ashok sir. Thank you very much for your time and nice presentation.
Thank you so
Narpita
much.
ma'am,
Yes, sir.
over to you.
Thank you, sir. Thank you for the wonderful session. Thank you
Thank
for
you,
sharing
madam.
your valuable expertise with us.
Yeah, madam. Thank you. Yeah, sir. Can I stop sharing?
Okay, sir. Okay, sir.
Yes.
So we shall proceed to the session 8 of day 4 by Dr. Shikhar Gupta sir from Synopsys India Private Limited, Bangalore. Shikhar ji,
For making me presenter.
Arpita madam, your voice is very low or not audible, it seems.
So is
Shikhar
it
ji,
audible
if you
now?
have joined us, please raise your hand so that we make you as presenter. Please raise your hand.
Sir, is it audible now?
Now it's okay, ma'am.
Okay.
But in just 1 or 2 minutes, let's.
Okay.
Okay, ma'am. Sir has joined us.
Sir, Shikhar sir, is my voice audible?
Yes, ma'am.
Sir, please
You're audible.
raise your hand, sir. Please raise your hand so that we will make you presenter.
Good evening, sir.
Good evening, ma'am.
We're delighted to have you again for this session.
Yeah.
I would like
Thank
to
you.
give a brief introduction to the participants who have not earlier joined. So we are honored to have Dr. Shikhar Gupta for this session, who is currently working as staff engineer analog design in IPG interface PHY team at Synopsys India Private Limited, Bengaluru. He has over 10 years of research and industry experience in the field of VLSI design. He obtained his PG degree in VLSI design from JC Bose UST, YMCA Faridabad, and PhD from NIT Kurukshetra. His research is on spacer engineered advanced underlap MOSFETs. He published 12 articles in SCI journals and conferences. He has in-depth knowledge of programming languages like VHDL, Perl, and software tool proficiency like Synopsys, CentOS TCAD, Synopsys Custom Compiler, Cadence Vertiso for digital and analog circuit design and layout design, Xilinx, and LT Spice. I hope his expertise will surely enrich our learning component. Sir, I would like to invite you for this session, and please share the presentation and continue with the session, sir.
Thank you, ma'am, for the brief introduction. Good evening, all
Thank you,
of
sir.
you.
Good
Thank you,
evening, sir.
ma'am. Thank you, Rao, sir. Let me present my screen.
Okay, sir.
Is the screen is visible for all of you?
Yes, sir. Yes, sir.
Yeah. So, hello, everyone. This is Shikhar Gupta. I'm currently working as a staff engineer in Synopsys India Private Limited. This is my second section in this ATAL FDP. So today evening, I'm like to present over an overview of DDR5 memory interface. So let me give a very slight description of the DDR5. What is DDR5? As everyone knows that DDR means double data rate. It means we are sending the signal from the both positive and negative edges. Okay, so what are the signals which is giving to the RAM? That are the DDR RAM, like DDR RAM, SRAM, DRAM, E square RAM, all are these RAM categories. So what is PHY? PHY is the physical layer interface which is responsible to connect the RAM or DRAM uh, to connect RAM or DRAM to the microcontroller or the controller, in general say to the controller. So we are going to, it's a huge big topic, so I'm going to describe in a very brief manner in today's session. So let we go to the introduction of the DDR5. So what is DDR5? DDR5 stands for the double data rate physical layer interface. So that physical DDR is represent double data rate, and physical layer interface we generalize acronym as the PHY. So it's a specialized hardware block which is in the digital system, which is responsible for the interface between the memory controller and the double data rate memory devices. So this is the GPU or CPU, or GPU means that whatever the graphic cards we are using, CPUs, or even the mobile processors also. This is the memory controller. This is the RAM. So it is a physical layer, whatever there is, because if you have ever opened your laptop, you have seen that yeah, you have a separate section for the microcontroller in the motherboard, and there is a separate section for the RAM. So to connect the microcontroller with the RAM, we need the DDR5s. So its main purpose to translate digital signal from the controller to the precise electrical requirement by the DDR memory, or it's a vice versa. It's not a single channel, it's a dual channel. That signal is transmitted from PHY to controller and controller to PHY in both phase. And it is one of the critical component in the memory subsystem because it serves as an interface between the memory controller and the DDR memories. So what are the main objective of the DDR5? Few objective is the signal integrity, then the physical interface, then the protocol transmission. Signal integrity and timings means that signal to be properly aligned. We are not have that much penalty that we are sending a signal at t second, and we are receiving at the microcontroller, we are sending a signal from the RAM or SRAM at t time, and we are getting at the microcontroller at t plus 2 nanosecond or t plus 1 millisecond or t plus 2 milliseconds. So it's a huge delay. Why? Whenever there's a delay, there is a huge power loss. And whenever the power loss, there is a huge risk of the burnout of the chip. So to maintain that signal to be properly aligned between the microcontroller and the RAM and the vice versa, DDR5 is responsible for that. Also, to meet the timing, also that signal should be proper. There should not be any delays. Like we are sending a signal from microcontroller to the RAM. The rise time of the clock and the fall time of clock is supposed to be a t nanosecond. But while receiving at the RAM, that rise time and fall time is t plus 50 nanosecond. That I can't afford. But because of this, lots of changes going to be happen. There is unnecessary glitches. There is more capacitances. So that will ultimately lead to the power consumption more, and there is huge risk for the data loss. So phi is also responsible to maintain the signal integrity and the timings. So also also going to operate at the high speed, which is required at high speed. If you have seen nowadays, if you go to the mobile market, you have seen that we have a SRAM of LPDDR5 or LPDDR5X that Xiaomi mobiles has like that, or Apple mobiles has like that, and even the Qualcomm processor are using the LPDDR5X. So LPDDR5X is a DDR technology, low power double data rate. 5X is the generation. So it operate at 8533 megahertz. That clock frequency is that huge. So we can't afford a minimal glitch, because if we have a delay, then in between the delay, in between there is that some clocks may pass on. If some clocks is passed on, then there is a huge risk for the data failure. So phi is also responsible to maintain the timings and the signal integrity. Another objective is the physical interface. So it provides the physical connection to the DDR memory, which handling the analog aspect of the communication, such as voltage level, impedance matching, and the termination. So for the analog communication means that radio communication or the mobile communication. What are the physical connection at the outside, that the human interface, that whatever the pins, what are voltage pins, what are the signal incoming signals, outgoing signals, that phi is responsible for those also. Also, one of the objective is protocol translation. The phi convert the controller's digital protocol, often from DFI DDR. DFI DDR means DDR phi interface. So DDR phi is double data rate physical layer, and DFI is DDR phi interface. So PHY instant for the F, and I instant for the interface. So phi convert the controller digital protocol, that microcontroller digital protocol, into a signal required at the DDR memory, because it is responsible for the communication between the uh, controller and the RAM. So it is also responsible to follow all the protocol related transactions. Now, other functionalities like data serialization and deserialization. So data serialization, deserialization means that, for example, the USB. So whatever it convert that parallel data into the controller, from the controller into the series for the memory, and vice versa. So how we use the USB? We take the USB, we put it insert in the USB slot of the either the laptop or the computer or the tablet or the even in the mobile phone. So it is to and fro data. Okay, we can copy the data from the computer to the USB or USB to the computer. So phi is one of the functionality of phi is to convert the data either from controller to memory or your memory to the controller into the serial data streams. Also, clock generation and distribution. It manages the generation of the clock. So clock generation distribution means the clock generation at the controller and the DRAM or SRAM level. They should be synchronized. There should not be any delays in the clock. Suppose at t second, first rising edge appears at the controller, but it should not appear as t plus 1 nanosecond at the RAM side, SRAM side or DRAM side. So there should be a proper clock generation and the clock, because there is a one source in any hardware, there is a one source of the clock. So the clock distribution is also responsible, is there is also responsibility by the PHY. That clock across all the memory is totally governed by the PHY. There should be a proper clock distribution. And also that other functionality is driver and termination control. It adapts the output driver and on-time termination to match the memory requirement for different data rates and the supply voltages. Power management, it support low power. Like we can't afford that nowadays. We have a laptop which delivers a less power. In the earlier generation, like 10 years back, we have a laptop which delivers the high position which has a higher power dissipation. So as the technology increases, as the architecture increases, so there is a huge demand that power should be low. Why power should be low? Because the all, at end of the day, the consumer electronics is increasing day by day, day by day, day by day. So if each device deliver more power, then there is a global risk of the weather. Like if you heard that in few months back, uh, Ghibli, which is a application in the chat GPT. So if people are running that application continuously, because of that the server get heat up and they need more uh, cooling agents to cool down the servers. Because of that, the temperature, that huge power is distributed across the globe. So there is a huge impact on the global warming and global climate impact. So power should be managed in terms of that low power should be dissipated by the fire, by the memory. Also it all support for the multiple configuration, like memory types, data rates, supply voltages, operating temperature. So there are many functionalities of the fire. What is the role of fire in the memory subsystem? Like it enhances the performance. Like phi is responsible to achieve the high data rates and low latency required by the DDR standards. Like what are the DDR standards? I'll take it later, but in the that DDR standard, DDR1, 2, 3, this is the generations, that DDR1, DDR2, DDR3, DDR4, DDR5, DDR, LPDDR. So DDR means double data rate, LPDDR means low power double data rate. 4, 4x, 5, 5x, 6, these are the versions, these are the standards that upgraded. So and why it is being discussed? Because over the generation we have increased the frequency, we have reduced down the power. So each generation has a particular architecture, and that architecture has a particular limit to operate. Like LPDDR5X going to operate at 8533 megahertz. DDR5 is going to operate at 9600 megahertz. So these are the significance of the phi in the memory subsystem. So why it is subsystem? Because the SRAM, DRAM are the one part of the memory. Phi is another part of the memory. So it is called as the subsystem. And it is also responsible for signal integrity, as I already told in the earlier slide, that proper phi implementation ensures signal integrity. It ensures that signal to be properly aligned across the memory, and it should have the minimum noise. Minimum noise means for any external signal the clock won't deviate, and it has the minimum timing error. Minimum timing error means the rise time and fall time should be as low as possible. It should be properly aligned, okay, across the memory, across all the systems of all the subsystems of the memory. Why it is why the clock is need to be proper? Because to maintain the operation of the speed, because it's a very high speed operation. So if there is a very small amount of the delay in terms of the nanosecond, for public domain, nanosecond is a very small term. But if we go to the subsystem level, the nanosecond delay is a very huge. So that nanosecond delay is going to pass one or two clocks. So if one or two clocks is going to pass, suppose if the signal is to be, the output of the inverter is to be zero at a particular time, but it is achieving a zero at t plus 1 nanosecond. So there is a huge impact over the performance of the circuit. Also, the technology adaptation, that phi adapt to different process technologies and foundries. Like there are very foundries across the globe, like TSMC has different foundries, Samsung has different foundry, Intel has different foundries, global foundries, UMCs. There are many foundries. Foundries means whosoever is are fabricating the chip, the end product, like motherboard or USB drives or flash drives or microprocessor, microcontroller, whatever it is. So these are the foundries. So it should be properly laid. It should not be like it is going to support for a particular foundry, it is not going to support for the other foundry. It is a global, so it should be adapted to all the foundries. Also the subsystem integration. So it means that phi provide the guidance to interact between different porting teams, hard micro sizing, placement, routing, and ensuring seamless integration with all memory subsystem. It means that wherever the controller and DRAM are connected through the phi, so there is a proper interaction in between the controller and the memory, and also with the outside world. That the outside world means the end user pins, whatever the end user pins we have. So moving ahead, what are the contribution to the functionality and the performance? So data throughput, for because it has a high speed, it works in a high speed operation, and low latency is required, and the maximum data is passed through from the memory to the processor or processor to the memory. Reliability, that it should have a robust operations. So it should not be any it should be reliable for all type of design structures. It should not be like particular design rule that it will work for a particular type of controller or particular type of RAM. Scalability means for the when the generation is advancing, like DDR generation is advanced from the DDR to the DLP, DDR6, DDR, DDR2, DDR3, DDR4, DDR5, LPDDR4, LPDDR4X, LPDDR5, LPDDR5X. So that as the generation is passing on, so it should support all the generation. So there is one particular file for each generation. if the generation change, the architecture of the controller, architecture of the RAM is changed. So the architecture of phi is also going to change. So that phi has that advantage to scale up or scale down themselves depending on the DDR family's requirement. So let's get to the what are the DDR5 standards. So DDR5, LPDDR4, DDR4 DDR5, LPDDR4, LPDDR4X, LPDDR5, LPDDR5X, UCI, Universal Chip Select Interconnect Express. UCI means the Universal Chip Select. I talk to this about later. So for the previous, I think 5-6 year or a decade nowadays, the DDR4 is widely used. Before that, DDR3 and DDR2 is widely used a decade ago. That this type of interface, this type of PHY is widely used across all type of computing. So DDR is used for the high high frequency operation in the CPUs, accelerators, GPUs. And LPDDR is used in the especially for the low power where the power delivery is very important, just like mobile. So we have a mobile, we can't expect that our mobile should deliver a more heat. So that power dissipation in the mobile should be low. So the LPDDR generation is for the especially for the low power and the end user product is the mobile, whereas the DDR is generally has more power, but it is generally used in the clusters, servers, computers, etc. So DDR4 is going to operate at 3200 MTS, whereas the DDR5 is going to operate at 8400 MTS. In case of the LPDDR is going to operate at 4267 MTS, whereas the LPDDR5X is going to operate at 8.533 gigahertz. What are the roles? So DDR4 has manages high speed signaling, and also every PHY has responsible for maintaining the timing closure and the voltage requirement of the controller and the RAM. So this is the among all the PHYs that it should meet the timing constraints. So also in LP, it has the additional responsibility for ensuring low power dissipation, whereas in the PHY, it is a universal chip select. So chip select means a small subsets of the ICs. So when it is being connected in a chiplet, so it's also adapted DDR signaling in for chiplet integrations. So what are the DDR? So these are the summarized tables that DDR4 is target applications, desktop servers. So servers that whatever the servers you have seen, the 16 core servers, 832 core, 64 core servers, even the gaming servers, gaming desktop. So DDR is widely used over there, and that operating speed is 32 MTS. And for the DDR4, it is scaled to the 8.4 gigahertz. The voltage is around 1.2 for around, this is around the similar voltage range across all the, excuse me, is there any, some background noises there? Any questions from anyone on over the call? Hello? Rao sir, can anyone is commenting? Hello? Hello.
Dear participants, please mute your mic. Dear participants, please mute. Shekharji, just 1 minute.
Yes, sir.
Okay, sir. Now you please unmute Shekharji and continue the session.
Sir, am I audible?
Yes, sir, audible. Please continue.
Yes, sir. So we are discussing about the DDR5 standard. So DDR4, the target is the desktop answer servers. So DDR4 is the old generation. So over there, the maximum speed is 3.2 gigahertz. So the voltage is 1.2 volts. So it has a high in density devices. So because it is being in the desktop and server, so their high density is very high. Whereas the DDR5, it is going to operate at the 8.4 gigahertz. Also, the voltage is around 1.1 volt. LPDDR4, LPDDR5 is operated at 4.267 gigahertz. It is used for the low power low power applications such as mobiles and the smartwatches. And if you have seen, there is a Amazon robot is there which is responsible for the cleaning of the room, so that the phi is overused there. The Google candlestick, the phi is used over there. So LPDDR5X is also used for the low power operation like mobile and the AI. So the operating speed is 8.5 gigahertz. The UCI is used for the chiplet or advanced packaging. So the variation of the clock frequency is quite varies and the voltage is quite varies depending on the DDR. So uh, let's move to the high level DDR memories. So at high level, that DDR are microcontroller, it's connected to the DDR5, then it is input output, it is connected to input output buffer, that clock generation is going to happen, and it is connected to the DDR memory devices, then power generation and utility and repeater cells. So these are the memory subsystem and memory system block. So what is the role of the microcontroller? So it acts as an interface between the CPU and the DDR memory system. So in the CPU, we have a motherboard. Motherboard has a microcontroller, correct? So microcontroller is responsible to get the communication between the uh, this is the memory subsystem. That all these are the components that memory, microcontroller, DDR5, input output buffers, clock generations, DDR memory, DRAM chips, whatever DMS RAM chips, power management, and utility cells. So these are the memory subsystem. So microcontroller is responsible to connect with the CPU and this memory subsystem. So it also manages the read write request, address mapping, refresh cycle, and the command sequences. What is the functionality? That it converts the processor request into the DDR protocol command. So if in every subsystem there is a protocol, so that data should be coming in this manner. So all this responsibilities is covered by the microcontroller. Then we have a DDR5 physical layer. So it serves as a bridge between the microcontroller and the memory interface, analog memory interface. What's its role? It translates the digital signal into from the controller to the electrical signal to of the DDR memory. It manages it also handles the signal integrity and timing and synchronization of the clock across the memory subsystem. And it has some hard macros like AC, X2, D bytes, master, and all soft components. Also, it handles the initialization and calibration training sequences. Next, we have the input output buffer. The input output buffer is responsible to drive and receive the signal to and fro from the DDR memory. Okay. So DDR memory set it also drive the signal, drive the DDR memory and also receive the signal from the DDR memory also. So next we have the clock generation and distribution. So clock is responsible for providing the necessary clock in the memory subsystem, and that clock should be synchronized across all memory subsystem. It like we this all the subsystem is there is one clock that this clock generation that clock is generated over here. So you can understand like this. So suppose we have a master pipeline, so water is flowing through there, so we want that all the sub channels, the water should be continue which flow with the same manner. So clock is that also has the same responsibility. Like you all the subsystems, the whatever the clock is going inside each subsystem, it should be properly aligned or properly synced among each other. When we have a DDR memory chips, so it store and receive data as requested by the controller. Then we have a power management and decoupling that it ensured the stable power delivery and minimum noise. Like if we have a external noise in terms of the thundering or human touch, so its role is to minimize the impact of the human body or thundering or any charges in the air or in the ambient environment which trigger the memory system. So its role to reduce down that effect. It also Then we have a utility and repeater cells. So it supports the signal routing and integrating across the cell. So clock is also responsible for the generation, distribution, and also responsible for the synchronous. But that it is all the path is not aligned. Like clock is at this place, memory at suppose clock is sitting over here, memory is sitting over here, and DRAM is sitting over there. So the path from DRAM to clock is less, and path from clock to the memory is more. So in between, there is a chances that the clock will degenerate itself. So for that, we have the utility and repeater cell. So that utility and repeater cells is responsible to strengthen the loose clock, whichever the lost their integrity in between the routings. So that utility and receiver cell are responsible for that also. So this is how it is connected. So CPU or is connected to the memory controller. Memory controller is connected to the DDR5, and memory controller is also connected to the clock distribution and generation channel. So DDR5 is connected to the utility and repeater cell. So since I already told you that DDR is also responsible for maintaining the synchronous operation of the clock among all the memory subsystems. So clock is generated from here to and it passed to the DDR5, and 5 is maintaining the uh, synchronization and integrity of the clock using the repeater cell. Then 5 is connected to the DDR DRAM, which is memory, and that power that whatever the decaps and memory management is there is connected to the DDR RAM. let's go to the basic of the DDR. So what is DDR? DDR is the double data rate. It's a type of synchronous dynamic random access memories. Okay, so that initially we have a static RAM, then we have a RAM, then we have a E square RAM, and now we have a synchronous dynamic random access memory SDRAM. So it is a type of SDRAM technology, DDR. So the key feature is that it transfer the data from both the rising and the falling edge of the clock. So previously we have a single data rate. So in that we can transmit the data only either in the rising edge or in the falling edge. So in that case, we have to deliver more that data for a particular clock period. Data delivered is less. When data delivery is less, then we need more clock cycle, and in this manner the power generation will be more. So ultimately in the wireless industry, one of the major objective is to reduce down the power as much low as possible without challenging the integrity of the data transmission. So for that we use the DDR. So it transmit the data in both edges, falling edge and rising edge of the clock, and that's why it is called as the double data rate compared to the so previously it was single data rate that the data is transmitted for a single edge cycle. Now it is transmitting for the double edges, so it is called the double data rate. Then we have a data transfer mechanism. So DDR, unlike the SDR, that single data rate, which transmit the data only once per clock cycle, DDR transferred twice per clock cycle. So this mechanism allows a higher bandwidth without increasing the clock frequency. So for suppose the clock frequency is 8.5 gigahertz. So for the SDR, the data frequency is 8.5, it's double. But the DDR, the data frequency is 8.5 gigahertz. So we have the double data frequency than the SDR. Then we have a generation of different generation of the DDR. Like initially DDR1 is DDR. Before that we have the SDR, then DDR1, then DDR2, then DDR3, DDR4, DDR5. Now it is LPDDR, which is nowadays is LPDDR6. LPDDR starts with LPDDR4, LPDDR5X. So LPDDR4 is the DDR4 extension, LPDDR4, then LPDDR4X, then LPDDR5, LPDDR5X. Now LPDDR6 is going on in the industry. What are the key components? One of the microcontroller, it manages communication between the processor and the DDR memory. It also handles the command address and the data bus. Other component is the DDR5, which is the physical layer. It converts the signal coming from the controller to the electrical signal for the memory device. So whatever the signal coming, the controller is distributing, the memory is not going to receive that signal. So for that we need a converter. So DDR5 is also responsible. One of other responsibility is to convert that logical signal into the electrical signal, which is transmitted to the memory, and vice versa also. Also, one other thing is the DDR chips. That's whatever the data is stored and retrieved. It is that DRAM is that bus. So every data is going to store in the DRAM, and if we want to retrieve any data, we need to access the DRAM. So DDR memory is organized into the banks, so each containing rows and column for efficient access and management. And the commands that such as read, write, refresh, all are used with the command controller. And the bus transfer means that data is transferred into the form of the bus. So whatever the bus are the protocols. So every PHY has some protocols that data should be received by this standards. So PHY is doing that conversion from whatever that it take the data from the controller, and it convert it into the some protocols and get to the PHY. What are the applications that I already covered? This signal integrity and timing, that we have to maintain the signal integrity and timing because it is going to operate at the very high speed operation. And since power should be as low as possible and there is no unnecessary power leakages in the memory subsystem. So applications are the computers, servers, mobile devices, graphic cards, network equipments. Nowadays, the whatever the microprocessor used in the automobiles, so this memory system is also going to use over there. Let's talk about the DDR organization. So dynamic random access memory, DDR stands for dynamic random access memory, is organized hierarchically to efficiently store and access large amount of data. And it has some cells which is responsible to storage each unit. Then what are the key components of the DRAM? So memory arrays, row data decoder, column decoder, sense amplifier, input output buffer, and refresh circuitry. So sense amplifier detect and amplify the small signal changes in the memory cells. Input output buffer, it responsible to interface between the DRAM chips and the external memory controller. Row decoder, it select which row to activate for read and write operations. Column detector, it is responsible to select which column is activated for the memory read and write operation. Memory cell array is the core storage area where all the rows and columns are organized. Refresh circuitry is responsible for periodically refresh the charges in each cell to prevent the data loss to due to the leakage. So whenever for in a cell any read and write operation is going to take place, so there is a huge leakage which is accumulated in that circuitry. Some charges is also there in that circuitry which is taken out in form of the leakage. So refresh circuitry periodically refresh each subsystem so that there won't be any leakage. If leakage is there, then there is a huge risk that data may lost over the time period. So what are the configuration the DRAM has? It has a channel, then rank, then bank, then row, then column, then the cell. Like for example, the DDR4 has the channel in the form of modern system which have multiple memory channel. It has one or more ranks. It has multiple banks up to 8 or 16. It has rows and column each containing thousands of rows like 16K rows and 1K columns. And each cell, that each cell is the intersection of rows and column, which is called as the one storage unit, one storage bit. What are the access sequence? Active commands, read write command, how we access the DRAM. Active command, activate command, that it send the microcontroller to activate on a specific row, that this row should be selected, that that microcontroller send a signal to the DRAM that this row or this column should be selected. So whenever the row or column is selected, so that intersection point intersection point is the place where the data is need to be retrieved or data is need to be stored. Read and write command, that controller issue read or write command to access the particular column or row. The pre-charge command, that row is closed and pre-charged to prevent the bank or for the next operation. What are the DRAM module? So dual inline memory module contain multiple DRAMs organized into ranks and banks and interface with the system via the standardized decode connector. So let's talk about the timing parameters. So DDI memory relies on totally relies on the precise timing. Why the timing is so important in the communication of the DDR? Because it is going to operate at very high frequency. So if data is going to transmit or receive at a particular time period, if it is going to miss, then there is a miscommunication. So suppose the output is 1, but we are getting the output at 0 for a particular for that time instant. So all the communication will break. So that's why this is very more critical. The timing should be more precise to correct data transfer between the memory controller and the DRAM devices. And also the timing should be as minimum as possible, because if the timing is less, then the power generation is also less, and ultimately leading to that. Also not the power generation, also we are getting the output in more quicker time, so we receive the signal more quick. So that's why the timing interval should be varies between the read and write operation. So these are the key parameters of the DRAM. That TCK is the clock time. So it is the time, it's a period of the memory clock. And just like that, it's the reverse of the frequency. That frequency is the one by time period. So it's the reverse of the clock frequency. So it set the base timing for all other parameters. So if it means lower the clock cycle timing, it means that frequency is, since clock is less for 1 by frequency is high. So it means if frequency is high, it means the data is going to transfer in a much higher speed. Other thing is TRCD, row to column delay. So it is the time activate, it is the difference of time between the activating a row and issuing the read write command to a column in that row. So it should be as low as possible. If it is going too high, so it will affect the latency of the DRAM. Then we have a low pre-charge time, TRP. So low pre-charge time means it is the minimum time required to pre-charge or close an open row before opening another row in the same bank. TRS. So it is the row active time, minimum time a row must remain open to ensure data can be read or write without its pre-charged. TRC, row cycle time, minimum time required for the successive activation of same row. So it is the sum of the row active time and pre-charge time. And we have a CS latency time. So it is the time between issuing a read command when the data is available on the data bus. So it directly affects the read access latency. If the TCL is less, then latency is, the data is going to deliver in a faster manner, and the latency of the DRAM is high. TWR stands for the write recovery time, is the time required after a write operation before a pre-charge can be issued. TWTR, read to write delay. So minimum time between the write command and the subsequent read command to the same bank group. So it should be as low. If the read command, write command, that time period is low, so there is a quick execution of the data transfer inside the for in the same bank. TCCD, column to column delay. So minimum time between the two consecutive column command in the same bank. So this should be as low as possible. So all the timing parameters should be as low as possible. Now we have the 4 activated window time, that time window in which a maximum of 4 activate command can be issued to a different banks. Refresh interval or refresh cycle time is the time between the refresh command and time required to complete a refresh. And what are the importance and performance over the DRAM? So like parameters like clock cycle and row to column delay and precharge time, they directly going to affect the data transfer. So if it is less, then data is going to be quickly accessed. So if, and also the bandwidth is going to define with this with the clock to cycle clock cycle time, row to column time, and column to column delay. So it also allows they allows more operation per second, increasing the memory bandwidth. So if there are more operation, then clock will deliver, that data will be delivered higher for each particular cycle of a clock. Power consumption, some parameters like refresh interval time, 4 active window time are set to manage the power and the thermal units. Data integrity, like parameter like row active time, recharge time, that ensure data is correctly written and read and retained and preventing for the corruption. Now, what are the DDR bus transfer? The process where the multiple data words are transferred consequently in response to a single or write command, single read or write command. So this is the bus transfer. How it is going to work? So DDR memory technology it is going to support 2, 4, 8 and the multiple. So like in DDR2 the burst length is 2, 8. DDR3 it is also 8, DDR4 it is also 8, and also in DDR5 it is 16. So it means that 8 for each read or write command, 8 consecutive data words can be transferred. So with the advance of the architecture, like this burst length will define how many data is going to transfer. Burst sequence. So when a read or write command is issued, the memory device outputs or accept a sequence of data words in rapid succession. So what is the how the DDR is going to work in the bus transfer? DDR memory transfer data on both the rising and falling edge of the clock signal, effectively doubling the data rate compared to the single data memory. Why we use bus transfer? So it increases the efficiency by transferring multiple data per command. The memory bus is used more effectively, reducing the overhead of memory command and address cycle. And the bandwidth, that because it is used in the DDR technology, so bandwidth is also going to increase. Why? And it is also going to compatible with the memory controllers and the processor designed to work with the bus transfer aligned with the cache line size and the data perfection mechanism. So like earlier told, that DDR3 has a burst length of 8. So uh, it means for each read and write command, 8 consecutive data is transferred over a clock cycle. So these are the data rates for each generation. So DDR first generation is the DDR. Before that is was the SDR. So the DDR it is 200 to 400 mega transfer per second. This is the data rate. The mega transfer data per second, and the clock is 200 to 200 megahertz, which gives the maximum bandwidth of 1.6 Gbps. DDR2 increases the flow of data from 400 to 1067 or 66. Somewhere it is written as 66, somewhere it is 67. Both are same. So it is a mega transfer per second. Clock is since the data is passing more, so clock frequency is also going to increase from 200 to 300 megahertz with a maximum bandwidth of 8 by 8.5 Gbps. DDR3 has a data rate of 800 to 2133 Mbps with a typical clock frequency of 100 to 1067. First time they in DDR3 the we are achieving the clock in the terms of the gigahertz. It is achieving to 1.067 gigahertz with a maximum bandwidth of the 17 Gbps. And DDR4 is going to transfer up to the 3.2 Gbps data and with a clock frequency of 1.6 gigahertz and getting the maximum bandwidth up to 25.6 Gbps. Now, current technology is DDR5, which is delivered the data up to 8.4 Gbps with a typical clock frequency of 4.2 gigahertz meant and achieving the bandwidth up to 67.2 Gbps. So as the technology, this is the voltage and signal evolution. So with the generation, different generation, voltage level is also going to reduce. Like for DDR1 to DDR5, DDR1 is 2.5, DDR2 is 1.8, DDR3 is in between 1.5 and 1.35, DDR4 is 1.2, DDR5 is 1.1. In case of the LPDDR, I did tabulate over here that LPDDR is going to operate that LPDDR5X operated at 0.85 and LPDDR is operating at 0.75 also. So in the DDR memory subsystem, we have the data queue and the data strobes. The data is transmitted by the queue and we have a strobe signal. So what are the role of the data queue? Data queue refer to the data lines or pins in the DDR memory system where the data strobe is the dedicated strobe signal associated with a group of the DQ line. In each DQ, pins carries one bit of data between the memory controller and the DRAM during the read and write operations. And DQ data strobe is used to synchronize the timing of data transfer on the DQ line. What are the functionalities of both? That DQ lines are used to transfer actual data payloads, whereas the DQS is generated by the memory controller during the read-write operations by the DRAM and read operation by the DRAM. Sorry, read operation by the DRAM and write operation by the memory controller. The DQ pins determines the data bus width. For example, that 8, 16, 32, and 64. So these are in the number of 2 raised to the power. So 2 raised to the power 3, 4, 5, 6, 7. And it DQ also the data is transferred for both rising and falling edge of the clock, effectively doubling the data throughput through compared to the single data rate. So DQ's transmission both rising and falling edge indicates when the data on DQ is valid and should be sampled. If it is and it is also responsible to sample the data. So strobe based timing is essential for high speed DDR operation where clock skew and signal integrity can make traditional clock based sampling underline. how this DQ and DQS is going to operate and interact in between in the DDR. So in the write operation, the memory controller drives both DQ and DQS signal to the DRAM. Data on DQ and is aligned with the edges of the DQS. So the DRAM uses the DQS signal to latch incoming information from the DQ line. During the read operation, the DRAM drives both again. So for every operation, either it is a read operation and write operation, the memory controller or the DRAM controller drive both DQ and DQS signals to the DRAM controller or the memory controller. So it's a vice versa operation. It's the to and fro operations. So during the read operation, data on DQ is also aligned with the edges of the DQS. The memory controller uses the DQS signal to sample the data. So previously the DQS signal to latch the incoming data from the DQ line in the write operation. During the read operation, the DQS signal is used to sample the data from the DQ line. So both DQ and DQS operate at the same operating frequency. So it should be same. Otherwise, that if both are going to operate at different frequency, then the sampling of the data during the memory controller to the during the read operation or the uh, latching the incoming data during the write operation is different. So both should be operate at the same frequency, and data is transferred on both the rising and the falling edge of the DQS, enabling the DDR operation. Otherwise, if it is not going to operate at both the rising and falling edge of the DQS, then it is the SDR. So for the DDR, both rising and falling edge, the data should be transferred at rising and falling edge of the DQS. Also, this mechanism allows for higher bandwidth without increasing the clock frequency. The timing is also one of the critical factor in the DQ and DQS operation in the DRAM. So there is a precise alignment of DQ and DQS for the reliable data transfer. So DDR5 do the training and calibration of read and write operation to ensure the proper timing alignment between the DQ and DQS. So one important terminology is the timing budget. So in timing budget, we have analyzed the operation of DQ and DQS, read write operation of from DQ to DQS to configure the account at different PVTs. Suppose DQ and DQS is aligned for a particular PVT, like ideal PVT is the room temperature and the nominal voltage. Suppose the nominal voltage for a particular DDR5 is 1.05 volt. So it is going to operate at 25 degrees Celsius and the typical corner, and the timing is aligned, but it is going to fail at different timing. So we have to observe for all the PVTs whether the read write operation of DQ to DQS is same. So let's talk about the DDR5 architecture. So let's get what is the difference in the controller to 5 or to the DRAM. So what are the role of the let's talk about different roles. So controller manages all the memory requests from the CPU to other subsystem masters. So there are many subsystem masters like clock is generated at the PLL, and we have a PHY, and we have a input output buffers, we had a utility cells, repeaters. So the controller manages all the memory access requests from the CPU or other subsystem masters. So memory request means the memory read or write operation from the CPU to others. So it also translates the high level read write request into the DDR protocol commands. The phi act as a bridge between the digital logic of the controller and the analog electrical interface of the DRAM. So the output is that controller uh, get the request from the CPU. So it converted into some digital logic. Then phi convert that digital logic to some particular protocols to the analog and the electrical interface of the DRAM. So that is the role of the phi. And DRAM is the physical memory that store and retrieve the data during the write and read operations, vice versa. What are the functionalities and responsibilities of all three? So controller schedules and arbitrates memory accesses. So it issues DDR command like activate, read, write, refresh, all the command, whatever we have going to give to the DRAM is given by the controller. It handles address mapping, like which row or which column is going to be activated or which bank is going to be activated so that a particular operation is retrieved from or stored at that particular cell. It manages timing constraint and protocol compliances. So the timing should be proper among the memory subsystem. So it interfaces with the phi using a standard logic digital interface. What is the role of the functionality of and responsibility of the phi? It converts the digital command data from the controller into the electrical signal from the DRAM and the vice versa. So controller gives digital command, phi convert into the electrical signal to the DRAM. Similarly, DRAM give the electrical signal to the phi convert it into the digital commands and send back to the controller. It also handle the timing calibration, that write labeling, read labeling, read write labeling, that read write labeling means that the timing of the read, not the read time, that at the time that suppose a read operation to be executed at t, the write operation will be executed at t plus delta. So it also handles the uh, timing calibration. It also manages the signal integrity and the impedance matching and termination among the memory subsystem. It performs training routine to ensure a reliable high-speed operation. Uh, it performs training. It implements hide macro of high-speed input-output and analog functions. And what are the DRAM operation? It receives the electrical signal from the phi in the forms of commands, address, and data. It execute memory read, write, refresh operation as per the DDR protocols. It going to store data uh, in the memory cell by the organized cell by the organized row, column, and the banks. And it return the requested data to the phi during the read operation. So CPU and the CPU or a master system issued a memory request, which is the read or write request. The control re receive the request, translate into the DDR protocol, and send it to the address. Send it along with the address and data to the phi. Why address is important? Because so that the phi will understand which bus we need to send, or we need to retrieve the data from which bus, or we need to send the data to which bus. Phi convert the digital signal from the controller into the appropriate electrical signal, perform the necessary timing calibration, and drives these signal to the DRAM. And then DRAM receive the signal performs the requested operation and send back to the PHY. Then PHY convert the received data from the DRAM back into the electrical form and pass to the controller. Finally, the controller deliver the data to the CPU subsystem or master or for the read operation or complete the write operation. In short, controller manages the memory protocol and scheduling. PHY handles the physical signaling between the controller and the RAM, and DRAM is actually a memory device which is responsible for storing or retrieving the data. So, what are the various blocks of the PHY and their functionality? So phi is responsible, as already depicted, that phi is responsible for the electrical and logical interface between the digital controller and the physical medium that connect to the DRAM or other devices. What are the key blocks? Data path logic, command address logic, input output buffers, which is the input output means the transmitter and the receiver. DLL, PLL, delay flash loop or phase lock loop, training and calibration, power management decoupling, testing and debug, configuring and control registers. So data path logic, it handles the serialization and deserialization of the data between the controller and the RAM, including the data alignment and the masking. DQ and DQS and DM are the logics in that data path. Command address path manages the transmission of command address and control from the controller to the RAM. Input output buffer, it converts the digital signal to the appropriate voltage level for the DRAM interface, and similarly convert the voltage level into appropriate digital signal connect to the controller. It also output the driver input. It has output driver, input receiver on-die termination control. So PLL or DLL, phase lock loop and delay lock loop, it generates the precise internal clock aligned for the data and the strobe signal for accurate timing. So that clock is being synchronized using this PLL and DLLs. The timing and calibration logic, it performs the initialization routines such as the writing operation, reading operation, impedance calibration across various PVTs. Power decoupling, that it manages power delivery, decoupling and noise isolation for sensitive and analog input output circuit. Test debug logic, it support built-in test case, loopback and scan test features for manufacturing and bring up, so that in future there won't be any is there any failure. So configuration and control register to store 5 configuration setting, training result and status information assembly for the controller or firmware. So this is how it is going to work. That controller, it send back to the data logic, it's connected to the DRAM, and this is the command and address part. It is also connected to the DRAM. That command and address path is connected to DLL, then the training and calibration, then the power management, and the testing or debug logics and the configuration registers. DDR5 clocking structures. So key components in the DDR5 clocking, it is very critical for achieving high speed, reliable data transfer between the DRAM and the controller. So there are some of the key components: reference clock input, PLL, DLL, clock distribution network, request generation and alignment, training calibration, CDC logic. So how it is going to work? That reference clock enters into the file is fed by the PLL. That clock is generated at the PLL and it is entered into the file. Then in also the PLL also generate the high speed clock for the DDR operation. The DLL all generate the clock for the delay adjustment for DQ and DQS and the DQ alignment. Then clock distribution network routes clock to all necessary block, maintaining low skew. Training logics uses DLL to calibrate timing during the initialization read-write labeling. CDS logics ensure safe data transfer between controller and the 5 clock domains. And finally, the DQS operation is synchronized with the clock for accurate data labeling. So where the few operations that what are the right path, what are the read path. So right path is responsible for transmitting data from the memory controller to the DRAM during the write path. So what are the key component? Controller interface receive the write data, address, and control signal from the memory. So memory gave that this you have to select this row, this column in this bus, which is pointing to a particular cell, and that write operation is going to happen and at that particular cell. And it is the parallel operation, so it means that we can write data parallelly. Uh, that data path synchronization, that serializer masking alignment. Serialization convert the parallel data into the controller into the parallel data from the controller into the width and the format required by the DRAM. Masking applies data mask signal to selectively write data. Write FIFO buffer temporarily stored data to handle the clock domain crossing and bus transfer, buffers data to match the timing requirement. DFI interface, that DDFI interface, that it standardizes interaction between the controller and the file. DLL and PLL generate the signal and align internal clock and DQS signal for the precise timing. DQS generation logic create the data stop and signal used by the DRAM to latch incoming data. Input output buffer drive the data mask and strobe signal into the DRAM interface. Training calibration perform the read light labeling during the initializing to align DQS with the DRAM clock. Rao sir, I think because of the time proximity, can we stop here and bring up the audience question?
Yeah, if you conclude, then it will be open for question and answers.
Okay, so let's open for the question and answers because already 5 to 10 minutes is still there for the call. Okay, I'll take 3-4 slides more, then we will conclude.
Okay, sir.
Okay, sir. So what is the functionality and the data flow? So data reception, that as already we have seen that memory controller issues the write command and present data, address and controller to the signal, and data buffering in the read FIFO to handle clock domain crossing and bus mode. Serialization and formatting parallel data is serialized to match the DRAM interface weight. Clock and strobe generation, DLL and PLL generate the required clock and DQ signal. Right labeling logic also DQS is phase aligned and DRAM clock for accurate data latching. Data transfer, I input output buffers in terms of the receiver and transmitter drive the DQ data, DM and DQ strobe signal onto the DRAM interface. What are the DDR read path responsible for receiving high data from the similarly like the read path, read path has the reverse operation. What are the command and address path? So the command transmission sends control signal that defines the type of operation, whether it is a read operation, write operation, pre-charge operation, activate operation, address or transmission. So it's send. So three types of transmission is there: address transmission, which column, which row, and which bank is going to select. First, the bank is going to decide, then row and column is going to selected, so that a particular bit is selected in the memory. Whatever the read and write operation will be done after that. So first is the command or first this is the address transmission, then the timing alignment that ensure that the command and address signal are properly aligned with the DRAM clock. What are the main component? Controller interface, command address logic, DFI interface, input output buffers. Just like the read operation, this is the read and write operation, this is the address path operation. So let's take the audience question. I wind up over here.
Okay, thank you, Shekhar
Hi,
sir.
sir.
Hi,
Thank
sir.
you, sir.
Okay, Murali sir, please go ahead.
Hi, sir. This is Murali.
Yes, sir.
Sometimes the clock will not get properly. That means the clock skewing is there.
Yes,
In the
sir.
situation, the data can be transferred, or is there any loss?
No, data is transferred, but at some particular instance where that another clock is coming, so data is lost. Suppose data is transferred at the T, should be transferred at the T, but data is transferred at T plus 1 nanosecond. But wherever the data is going to receive, it is going to delay again. So the receiver is not going to wait that for the T plus 1 nanosecond. So it that for that particular clock, the data is going to be missed. So we consider as a loss of the data.
After verifying that skew and resuming the skew only, then you can get the data. Meanwhile,
Yeah,
the
so
data is going to be lossy.
yeah, so just like for a particular instance that suppose the very best example in the Indian system or in the public domain, in a layman language, which I said that if we call an ambulance and ambulance should be come on time, then it will be the data is delivered on the time. If ambulances come after if some particular time when there is no need, that unfortunately the casualty takes place, so it means the data is lost. So you can consider that ultimately the ambulance is coming, the data is going to receive, but it should be, we should get the data at particular that time, so that the other stage where the sampling or desampling is going to take place. If it is a read operation or write operation, it is going to controller, or it is going to the memory. It is going to be changed, because for that clock cycle, if the data is skewed and receive some for two other clock cycle, but the at that clock cycle there is some other operation is going to takes place. The bus is changed, if the bus number is changed, or if the row or column number is changed, then the cell number is going to change. So that you can consider that data is lost and it is functionally incorrect. The phi is that memory system is not functionally well. Some question, I think, Rao sir over the call chat.
So what happens when the glitters are carried the clocks?
Yeah, so for that we have repeaters also, sir. The repeaters also responsible to to remove the jitters. All these. So each file have jitter corrections also in terms of the DC and DCD. So the and we it will check that we have the various series of components. It will check that there should not, that if there is a jitter, so it should not be past some threshold value. Before yeah.
That's also.
Okay, sir. Shekhar sir, there is one question in the chat. What are the challenges in a DDR system?
What are the challenges in the DDR system? So challenges means initially, if the old generation, we can consider that the uh, data rate is slow, the clock frequency is slow, the power delivery is more. So with as the technology, as the generation advances, so data rate is more. Now data in the DDR system, data rate is more, but the power and the power delivery is also less. But DDR we can't use for the low power application in the small devices where tablets you can consider mobile or smart watches. So over or the even for the automobiles where we can't provide that memory system, we can provide the customer to that memory system where we have to give the proper cooling system. So this is the disadvantage. That's why DDR is not used for the mobiles, and LPDDR is used for that also.
Okay, sir. One more question in the chat. What tools or simulation methods are commonly used to verify DDR interface timing?
DDR interface timing that currently Synopsys is using anti-nanotime and SIS Silicon Smart for configuring the DDR interface timing.
Okay.
Okay, so I can't say the other vendors what they are using, but for Synopsys they are using prime time or nanotime or SIS or the especially for the DDR interface, it is the NT and SIS,
Okay,
nanotime
sir.
and the Silicon Smart.
Okay.
What is the major research scope on this area?
Major. So for the DDR5, Synopsys is one of the key player to deliver the PHYs, not the DDR. I'm talking about the PHYs. So there are other companies, other competitors also. So we have different customers like Qualcomm. We have a customer, Xiaomi. We have a customer. So there are many customers for that, and other companies are also some like Intel also have their own DDR interface, but Synopsys is one of the key player to manage it for that DDR interface, DDR5 IPs.
Shekhar sir, what is the difference in the topologies from DDR1 to DDR5? I think latest technology is DDR5. Am I right?
Yeah, latest is DDR5, so it is going to operate at, if we're going to compare with the DDR1 at the operating voltage of 2.5, now it has a operating voltage of 1.05 at DDR5. DDR5 is going to transmit the data of 200 megabits per second. Now the DDR5 is going to uh, transmit the data, I think 3.2 gigahertz GBps. I'm not recalling. I just bring at that sheet. It is going to operate at that high data rate. So ultimately, data is processing at a higher speed rate, and the clock is also higher. That previously in DDR it is 200 megahertz. Now it is 4.2 gigahertz. Data rate is 400 Mbps. Now it is 8.4 Mbps. Previously, we are going to achieve the maximum bandwidth up to 1.6 Gbps. Now it is 67.2 Gbps. So as the technology or architecture is increasing, so we are also going to, the basic idea is that data should deliver in the more faster rate. So along with that, we are also getting more bandwidth, because bandwidth is calculated the data rate and the bus width. So we are increasing the bus width, and we are getting the more bandwidth.
Okay, sir. Thank you. Dear participants, any questions?
Okay, one question I am seeing over the chat box. Uh, what are the tools for simulation method for commonly used to verify? Okay, this is covered,
Sir,
I
already
think.
this is
Yes,
this is
sir. We
asked.
have
Yeah,
covered
this
it.
is
Hmm.
covered.
Okay, dear participants, if you have no questions, then shall we conclude the session?
Yes, sir. Yes, sir.
Okay, sir. Okay. Arpita ma'am,
Okay,
please
sir.
conclude.
Thank you, Shikhar sir. Thank you for sharing your valuable expertise with us. As we conclude
Thank you,
the
ma'am.
4th day of our 6-day faculty development program, we express our sincere gratitude to all of you for your active participation and engagement. A heartfelt thanks to the distinguished speakers of today, both the sessions, for sharing their valuable insights with us. Your expertise has truly enriched the today's program. And we hope today's sessions have sparked new ideas and perspectives that you can carry forward in your teaching and research practices. So we look forward to again seeing you tomorrow for another day of learning. Until then, thank you. Thank you once again.
Thank
Thank
you,
you,
ma'am.
ma'am.
Thank you, sir.
Okay, okay. Thank you all.
Thank you all.
Thank you, audience. Thank you very much. Thank you,
Thank you,
sir. Thank
Shikhar.
you, ma'am.
Thank you, Shikhar sir.